All right, this is Power Amps Part 2. If you remember the last lecture, we were talking about an AC load line. Let's draw a little picture again. And we were discussing Q point. So we've got IC, we've got VCE, okay, we've got an AC load line, and on that load line we've defined a Q point. So in the last example we looked at, we had shifted the Q point low on the load line, low current. Let's bump it up now. Let's stick it up here and talk a little bit about what's going to happen with our load line located here. So we've got, let's again define some points. We've got IC SAT here. We've got, oops, I'm sorry, that's ICQ. That's the Q point. ICQ. Okay, we've got IC SAT here. We'll represent as saturation current value. Okay, you can drop vertical here, put an axis here. Okay, and this is going to represent VCEQ. What else do we have? VCE cutoff. Okay, and if we look at our sine wave now, okay, our maximum amplitude of VCE and IC is limited by the saturation. Okay, so we've got a limit here. So our maximum, I'm not putting any values in, but our maximum swing, positive half cycle swing on the current here is, you can see it's limited by IC SAT. If we go over here, and I have to drop a, okay, zero here. We've got our limit here for VCE. So you're limited in the negative half cycle here. If we go, if our amplitude is increased beyond the saturation point, what happens is our transistor gets driven into saturation, and we get clipping. So we can say here our transistor is driven into saturation. By a further increase in input amplitude. All right, and we can show that. I can draw. I'm just going to draw it right down here. I think there's room. So draw another curve here. Characteristic curve, load line, Q point, whatever we want to call this thing. There's different names. They all sort of mean the same thing. Different terminology. So let's draw our AC load line. We've got our Q point in the same place. Approximately. Drop a line here. Okay. Drop one here. All right. So we've got our saturation point. I see sat here. Okay, we've got VCEQ. This is ICQ. This is VCEQ. I'm going to drop 0 here. All right, so our limit now, switch over to red. Again, if we try to exceed, if we pump up the input too high, we're going to get too much output, and it's going to get chopped off or clipped right here. Okay, so we're clipped on the positive half cycle for IC. For VCE, we're going to be clipped on our negative half cycle. So again, our transistor gets driven into saturation. If we increase the amplitude, increase the input amplitude, so our output exceeds IC sat. It just gets chopped off. So a little bit of an idea of how these Class A power amplifiers work. Now there's a couple other things we want to talk about. Let's start a new page here. Okay, we want to talk about power gain. They're power amplifiers, so yeah, there's going to be power gain. So we know in general, okay, gain and power gain is abbreviated as AP. It's power at the load divided by power in. So let's go quick, do some calculation review here. Okay, if you recall the general formula for power, it's V squared divided by R. That's one of them anyways. It's also I squared times R, V times I. So for AC power, voltage, you may recall this, is expressed as RMS. It's an RMS value. Okay. The output power delivered to the load using that formula above, I'm just going to call it PL instead of just plain old P. So it's PL is equal to load voltage squared divided by RL. Okay, the input power delivered to the amp. Okay, let's say that. Delivered to the amp is, we'll just call it Pn. Vn squared divided by Rn. Okay, so you can do some juggling. We have a formula in terms of voltage and resistance for PL, a formula for we got PL, we got PN, and we got this formula up here for AP in terms of PL and PN. So we can do some substituting and juggling. Juggling around mathematically. We said, again, AP is PL over PN is equal to VL squared over VN squared times Rn over RL. And we can say, since VL over VN now is equal to voltage gain AV, we can say our power gain is just AV squared times Rn over RL. Just some math. Now, let's continue. New slide. Okay, if you recall, for a voltage divider biased amplifier. Okay, Rn total, or TOT as the book calls it, is going to be R1 in parallel with R2, parallel with Rn base. We'll do an example in a minute. But R1 and R2 are discrete resistor values, okay? And they're used, again, to set up biasing. We've been using them all semester. And we can say for common collector, which we've been abbreviating CC, and a common emitter amplifier, Rn base, that's the resistance of the transistor configuration looking in at the base, is going to be beta AC times, we've been using the term little re, okay? This is for common collector, where that little re is equal to Re in parallel with RL, emitter resistor in parallel with the load resistor. And we said, this again is all review. I will be posting that 4 transistor configuration review I did in class when we started this chapter, where I talk about common collector and common emitter and some of this stuff. That'll be posted within the next day or so. We said Rn base was equal to beta AC times RC, and that's a little c. This is for common emitter, okay? And again, that's a little c, where that R little c is equal to RC parallel with RL. And again, this is for common emitter amp. Okay, we can do a quick example. Very simple. For a common collector amplifier, let's say, that has an input resistance of 10 k ohms and a load resistance of 100 ohms. Find power gain. Okay, I'm going to grab a new page here. So if you recall, a common collector amplifier has a voltage gain of approximately 1. So power gain is equal to the voltage gain squared times Rn over RL. So what's that? That's 1 squared times 10k, which is Rn in our example, divided by RL, which is 100 ohms, is equal to 100. So for a common collector amplifier, power gain is just the ratio of the input resistance to the output resistance. Okay, so that's pretty simple. Now there's a couple other things we wanted to find here. we want to define something called the DC quiescent power, Quiescent power. Okay, that gets abbreviated. You'll see that abbreviated PDQ. That's the power dissipation of a transistor. With no signal input. And all that is, PDQ, is just ICQ, Q point current, times VCEQ. This is by definition, so that's VCE at the Q point. Okay, and what this is an important number too. This is the maximum power that a Class A amp must handle. And the transistor's power rating, which is a spec, must exceed this value. Okay? All right. Another definition, another page. Let's talk about something called output power. Okay, we've already kind of talked about this. Okay, it's called P out. Okay, we said, if you recall, the maximum unclipped AC signal occurs when the Q point is centered on the AC load line. Okay, we understand why and what that means. For a common emitter amp with a centered Q point, okay, the maximum peak voltage swing is, let's say, VC max ICQ times RC. Okay. The RMS value, remember we said power is calculated using voltage and RMS. The RMS value is 0.707 times VC max. Okay, so the maximum peak and the maximum peak current swing is IC max. That's going to be equal to VCEQ divided by RC. Okay, the RMS value for that is 0.707 times IC max. Okay, so to find the maximum signal, power output, you use these values. Use these two RMS values. So we can say P out max is going to be equal to 0.707 times IC max times 0.707, this voltage times current, 0.707 times VC max okay. You get those 0.707s in there. Again, you do some math. You get P out max simplified is equal to 0.5 times ICQ times VCEQ. Okay. All right, and I will stop Power Amps Part 2 lecture